Kene Akametalu. I am a rising senior electrical engineering major at the University of California, Santa Barbara. And this summer, I had the privilege to work with Dr. Anthony Gribic here at the University of Michigan. The title of my project is called Extending the Range of Wireless Non-Radiative Power Transfer Systems. Now, I'm sure many of you are familiar with wireless power transfer, or wiretricity, as it's been so popularly referred to. Some of the applications of this include charging electronic devices such as laptops, or like in this case, a cell phone. You can imagine going to, let's say, Starbucks, where they already have like Wi-Fi or wireless internet, and rather than bring your cords and your chargers with you, you just literally have more or less your devices are getting charged for you wirelessly, and you don't have to worry about bringing all the clunk and clutter of all those wires with you. There are also other applications that you guys might not necessarily know about, but are also being worked on today as we speak. I'll show you a few right here. So the electronic devices, as I stated earlier, sorry about that. We also have applications in automobiles. So if you look at this cartoon here, what people are looking at now is they want to be able to put these mats underground that can charge your car, that can charge electric vehicles. So the idea is you have this mat underground, and you have a receiver at the bottom of your car, and when your car is parked, it can more or less get charged for you. Some other applications include robotics. They're thinking about using these systems to power either robots in the manufacturing, or also household robots such as the Roomba and other mobile robots. So with that, I just wanted to give you as an example of a wireless power transfer system. In this case, we have two resonant loops. I'll go into what the term resonant means later, but let me give you a quick explanation of how this thing works. So what you have is you have one coil here. A signal is sent through this coil, and and by Ampere's law, what you're going to get is you're going to get a magnetic field. And if this magnetic field is strong enough, and this second loop is close enough, this varying magnetic field can induce another current in this loop, and that's called Faraday induction. And what you have is pretty much you've had power transfer wirelessly from this first loop to the second, thus charging this light bulb for you. So I have a quiz for you guys right now. Nothing too serious. So what do you think would happen as I separate the loops and make them go farther apart? What would happen to the light bulb? Do you think it would get brighter as the two separated? Would it get dimmer, or would it stay the same? Okay, let's see what the answer is. So some of you probably, or most of you probably answered that it would get dimmer, which is indeed correct. Now I have another question for you guys as part of this quiz. What do you think would happen as the loops got, let me put the cartoon back on again. What do you think would happen as the two got closer together? Once again, would it get brighter, get dimmer, or stay the same? Many of you probably answered either stay the same or get brighter, but in fact, it actually gets dimmer. So I'll show you why that is. So first here, what we have is we're dealing with a fixed load wireless non-radiative power transfer system. What that means is that in our case, the load RL would have been the light bulb. Is that it's a fixed load. You can't change how it appears to be to the rest of the system. So what happens here is that this is more or less a circuit model of how our loops look. We have the source resistance, which is more or less the energy that the source wastes on itself. The resistance of the loop, which is energy that's lost to the loop. We have the capacitance, which is the physical capacitor that we put in the loop, which stores energy. And we have an inductance, which also stores energy and comes from the physical structure of the loop. And then the last key component is this L12 value, is mutual inductance. And that's pretty much relates to how the magnetic field is shared between the two loop structures. And on top of that, L12 also varies with distance. So as the two get closer together, they share more of the magnetic field. Therefore, you have a higher mutual inductance. And as you can see here, based on this model, what it predicts is that for a fixed load, what you get is a situation where at one particular distance, your efficiency is going to peak. But once you operate at any distance other than that, your efficiency is going to fall off. So these three curves represent three different loads, so that they're going to maximize the efficiency at different distances. But the one thing they have in common is that whenever you operate away from that distance that yields the maximum efficiency, the efficiency is going to drop off. So here, let's visit the board really briefly. I want to visit the topic of the circuit model a little bit more. So before I talk to you guys about resonance, and I'm going to explain to you guys what that is. So like I was saying earlier, this C, the capacitor and the inductor, they both store energy, which is bad. We don't want that to happen because if they're storing energy, that reduces the amount of energy that can make it to the load, which in this case was our light bulb. So we operate at what we call the resonant frequency, which is omega naught equals 1 over square root LC. If we operate at this frequency, what we get is that each loop resonates on its own. And effectively, what that means is that these two, the effect of this one cancels out the effect of this one. Therefore, you're eliminating the loop from storing energy, and you're freeing up more energy to make it to this load. And so in general, whenever you're operating a resonant loop system, you want to operate at this frequency. But what we also found out from this model is that in some situations, you can have your loop operate, you can have, rather than have each loop resonate on its own, you can get the whole system to resonate together at 2 additional frequencies, which is referred to as frequency splitting. I'll get back to my slides and give you guys a little bit more detail on what that is exactly. So pretty much what happens in frequency splitting is if you can have omega here is your frequency. So you have this equation, and it has 2 solutions. So whenever this equation can be solved, it has 2 solutions, and at those 2 solutions, your system once again resonates. But not each individual loop does not resonate on its own, but collectively the loops resonate together. And some pretty cool things happen when this is achievable. But the question is, when can you achieve this? And what our model predicted for us after we worked out the mathematics is that this frequency splitting phenomenon can only occur at distances shorter than the distance where the maximum efficiency occurs. So I'll make that a little more clear. So let's say, for example, I have a loop here and another loop here. And I design the load in such a way that the maximum efficiency occurs when the loops are 20 centimeters apart. Then what I'm saying is that if I bring this loop anywhere closer, whether it be 10 centimeters, 15 centimeters, 5 centimeters of separation, then that frequency splitting equation can be solved. And once that equation is solved, another cool thing happens. Our maximum efficiency that we get can be maintained. So let's say, for example, if we have the maximum efficiency occur at 20 centimeters. If we move to 10 centimeters and operate at one of those split frequencies, what we end up getting is that the maximum efficiency, rather than fall off as it did before, it levels off. And so our system can operate at this maximum efficiency for distances that are closer. Unfortunately, for distances that are farther apart, the best we can do is operate at the resonant frequency, and we get the same phenomenon where the curve falls down. This can be better seen in my slides here, once again. So as I was saying earlier, you can see for these 3 different systems that operate at different maximum efficiencies at different distances, the one thing that's common is that as we move to the left of that distance, or as we make the distance smaller, our maximum efficiency is kept. And so this is what the theory predicts based on the model and the mathematics that we did for the model. This is the prediction. So what the next step I had in this process was to confirm that the same way that that our mathematical predictions would also turn out that way. So what we did is we performed a simulation using Agilent's advanced design systems, and we did a circuit simulation. And what you can see here is that the straight line refers to more or less the mathematical solution, and then the circles refer to what we got from the simulation. And as you can see, they're 1-to-1. So it verified that the predictions that we made were indeed correct. And if you were able to frequency tune, that you can maintain that maximum efficiency for closer distances. So now let's revisit the question I asked before. Now with frequency tuning, as the bulb gets closer, what happens to as the loops get closer, what happens to the bulb? You can see that the efficiency, the brightness of the bulb actually does stay the same. That concludes it. So in conclusion, to give a brief summary of what I did this summer, I pretty much worked with a model that described our WNPT system. From there, I was able to make predictions based on how the system using circuit theory, and I verified those predictions using a circuit simulator. Then what I did after that was to model our actual loops in a software called HFSS and verify that our loops could indeed be modeled as this RLC circuit model. I would like to thank Professor Gribik for giving me the opportunity to work in his lab, my graduate mentor, Mohammed Reza, and I would like to also thank the SROP program, especially Mike Nazareth, David Hudson, Pat McCune, and Ebony Reddock for all the help that they've given us. SROP is a great program, and if any of you are considering going to graduate school, I would definitely recommend that you look into the program. Thank you very much for your time.